Morning, everyone. So today we're going to start with a new chapter. So last chapter, there's only 4 chapters, and this is the last one. So I already uploaded the material for this chapter, and so it must be about the same size as the other one, but it's substantially different. So some of you may know about this other way of doing statistics, which is complementary rather than different. It just adds rather than contradicts what we have seen so far. But nevertheless, it is a bit shocking at the beginning why we have to change the mindset a little bit to understand. So bear with me if you haven't seen this. It's going to be a completely different topic today. So it's just the introduction. So it's called Bayesian inference. So it's capital stands for Bayes. So the person who introduced it 100 years ago, or at least which started to do the first ideas. So that's where the names come from. So anyway, I think I'm going to start with an example. So as I said in the notes on the other side, so it's chapter 4 for Bayesian inference, and the first section is basically the simplest example you can ever think of in this type of courses, which is the Bernoulli distribution. Okay, so let me just start with that example, and then we're going to try to be very general in this example. So try to cover all aspects of this new way of doing statistics, which is Bayesian inference, and then we'll try to go back to the generality instead of doing it the other way around, because as I said, it's quite in many ways it's quite different from what we've seen so far. Okay, so I'm just going to draw some notation and some plots from this other side from the lecture notes. So, but I'm going to try to do the detail on the other one. So there is not much in the slides today because I'm going to write most of it. Okay, so let's just start in the way we have done it. So we have always a sample. We always have a sample of numbers from some distribution, and in this case it's just a Bernoulli distribution. So remember, Bernoulli is the simplest one. We only have 0, 1. It's basically success or failure, 2 categories, male or female, large or small, and the probability, it's the only parameter, in this case we call it theta, is the probability of being 1. Okay, so whatever that is what is being defined as 1. And the density, or we call it more specifically probability mass function, is this simple thing there. Sorry, this one. So it's obviously when yi is 0, then you get just 1 minus theta. When yi is 1, then you just get theta. And we assume we have an independent sample of size n. And from that density, and the assumption we are doing so far, and we basically going to keep it for this section, it's that theta star, it's unknown. So we have a correctly specified model. Remember that we diverted a little bit in chapter 3, and we assumed that we were going to have a mid-specified model or wrongly specified models. So let's go back to the situation in which the model is well specified. So I'm assuming that the generating process from this data, it is actually a Bernoulli distribution. Okay, so let's calculate the log likelihood, which is what we have so far, and then we just build up from there. First of all, the likelihood, and then the log likelihood. So let me just do that. So it's been a long time since I haven't done just a kind of a full exercise, so let's just do that today. So so the log likelihood, we have actually a notation we don't use much, which is L. So it's L of theta given our sample, okay? And this is, by independence, it's just the product of from I equals 1 to n, of this fyi, okay, given theta. Okay, theta in this case is not a vector, it's a number, so I'm not putting an underline underneath it. So let me just see, so we got the product from I equals 1 to n of theta yi, 1 minus theta, 1 minus yi. Okay, so remember the assumption of independence. It's basically what we always do. That's the one which basically we're going to stick, or we haven't stick so far, and then we're going to keep it until I say otherwise. So that's why it's the product, right? So the product of the density, the joint density of independent random variables is the product. But because of this is a simple enough density, and by the properties of the exponents, we got that this is theta. And I'm going to use a notation because it's easier to write rather than writing the whole thing. So I'm going to call it S. S is usually stands for a statistic. And then this is 1 minus n minus S of y, where obviously S of y it's the sum from I equals 1 to n of yi. Okay, so this is a notation. And again, why I'm doing that notation, just because in the notes I use that notation, and also it's just a little bit easier to write S of y rather than the sum from I equals 1 to n of yi. And remember the word S I used, it turns out to be this is an exponential family, so it's one of these S functions that I use in the exponential family, and S stands for a statistic. A statistic is just a summary of numbers, okay, as we usually know it in a colloquial context, not necessarily in statistics. Okay, so this is generic. I haven't given you values of anything of y, of the vector y. It's just what it is. So that's my likelihood. So that's the one there on the other side. Okay. So it is. Remember, the likelihood is, depending on how you look at it, is the joint density. But when we look at it as a function of the parameter, then is the likelihood. Okay. Actually, I should have said this. So this is equal. Let me just see if I have some space here. Let me just move this one a little bit down, just so that you don't get confused. And this is equal to the joint density of y given theta. But again, this is when you want to do probability operations, then you use it that way. But here we're doing statistics, then we have to use it in the way I described as the likelihood. Okay, so that's it. This is what we got so far. I'm not going to do what we have done because, I mean, we have done it many times. So we can calculate the Emily, right? We can think about the plotting the log likelihood. For example, I haven't even got the log likelihood. I just got the likelihood, but it's just taking the log. And then we can compute the maximum likelihood estimator. In this case, it has a closed form. Hessians and gradients and etc. And that's what we have been doing so far. So I'm going to go one step further today and change the mindset. And the mindset is, the quick reminder is that theta star is unknown. I know it's written there, but I just wanted to emphasize that. So theta star is the probability of 1, and in this context 0, I'm observing only binary variables. And I don't know how much it is. It's a number between 0 and 1, but I don't know what it is. So it doesn't look that very difficult. So I just need to have a kind of some sort of information to include in this problem. So imagine I got more information which is not the sample. Because what I'm assuming here is that my only information, it is the sample, and obviously the model. But let me just use a different color. So we got my sample, y, so this sample is a source of information. But imagine I've got some other information which could have been somebody. Imagine this is the probability of some event happening. And I don't know, it's going to rain tomorrow at around about midday. So this is something we can try to assess. We can have some historical data, and that is our y. That not may be independent, but doesn't matter for this situation. But imagine we got an expert on climatologist or something, and then he can give us a little bit of more information that he has using some other means. And then he come up with a plot like this. So imagine, so let me see. I think in the notes I use yellow. So let me see if I can find I'm just going to use this color. So let's just do the plot. So and here we have 0 and here we have 1. So imagine somebody comes and tells us this, okay? And this is theta. This is the axis of theta. And this is 1, okay? And somebody comes and tells us that his assessment, he or she, her assessment is like that. Okay? So they don't want to compromise themselves and say, it's going to rain tomorrow at midday. They don't want to say that. They just want to say, this is my assessment. So actually, let me just do it a little bit more extreme. Let's something like this, a little bit more extreme, so it goes like that. Imagine it just sticks to 0, not that goes up again. So this person doesn't want to compromise and say it's an event 0 or 1. He just wants to say it is very likely that, or it's actually not very likely, it's 50% or less the chance that this person assess to be possible. So it seems like a very fuzzy or not very general statement, but imagine this is what we got. So let me see. I'm just going to put the half here, obviously, somewhere there. So basically what this person's saying is that he or she doesn't think it's very likely that it's going to rain. It's something less than 50%. It's not exactly, because you see the curve has a little bit of mass after the half, but that's what it is, okay? So how can we include that information in the process? It's not a sample, right? So we cannot use probability theory in the way we have been using it, because it's not a y1 to yn as we're using it so far. It's just a distribution. Obviously, this integrates to 1, so let's just say that the integral from, and let's just call this f. I'm just going to call everything f, because it needs, depending on what we put as an argument, it's going to be clear. So the integral from 0 to 1 of f of theta now, d theta, it's 1. So it's a density, and obviously it's positive. So we got that f of f is just positive, let's just say. It can be 0, just in general. Maybe we don't want that later, as you will see, but imagine it's just positive or non-negative, and it integrates to 1. How can we include this information? So let me just write that question. So how can we include this in the analysis, right? Or in the inference. Remember, the word that we use is inference. And inference about what? It's inference about theta star. So this is a question mark. So the theta star, this person is making the assessment that is very likely to be between 0 and a half. But the data may tell me something else, right? Because the data is supposed to be something completely independent in the general sense from that. So, so this is what is called a prior distribution, and the word prior generally means that it happens before, but it doesn't happen before. It doesn't need to happen before. It's just that it's a separate information about the parameter. Okay, so this is called. Let me just start giving names. So this is the prior distribution. I mean, this is the density, but remember the distribution is the probability. Let's just call it like that. Prior distribution. Okay, so prior. Okay. Okay, so let's just try to do that. Let's just combine it. Let's just give it a specific formula. So let's use that one. So that formula there, which is a beta distribution, it is a distribution like that. It integrates to 1 between 0 and 1, and it's positive. So let's just use that one. Okay. So, okay. So let's just use that one. So for example, let's use. For example, let's assume that f of theta, it is of the form like that. So this is theta alpha minus 1, 1 minus theta beta minus 1 divided by b of alpha and beta. And let me just say something very important. Alpha and beta are just known constants. Both are positive as well. Okay, and then I'm using that color because I use color coding in the note so that we don't get confused which one is which. That function b is so-called the beta function. So you can write it that way. It just happens to have that formula. But something which is not completely obvious, but is going to happen, is that I'm going to stop worrying about the normalizing constants, okay? Because at some point they're going to be just impossible, and then let's just start to stop worrying about it just right on time. So, because they're going to be an issue, but it's an issue that we can sidestep later. So, in this case, I'm just going to give you the normalizing constant, which is 1 over this beta function, which is this formula, is the product of the gammas, and divided by the gamma functions, and divided by the gamma of the sum, okay? So let's just think about these three possible scenarios, okay? Let's just think about these three possible scenarios, the ones which are in the notes. Okay, so three scenarios. Okay, so let me see. I didn't call them anything. They're just bullet points. So the first scenario is alpha and beta is 3 and 19. Everything will make sense in a few minutes. Okay, let me see what else do I need. It's just the probability. Okay, so the probability of theta less than 0.3 is 0.97. And I'll draw some plots in a minute. Or at least I show them to you. The second scenario, it's 11, alpha and beta, remember? And the probability that we got between 0.3 and 0.7, it's 95, okay. And the last scenario is just the opposite, 19.3, I guess, yes. And the probability that theta is larger than 0.7 is 0.97, I guess, yes. And this is just roughly. So the letter, let me just write that at the top. This letter, which is not very well written, but so that you get used to, so this is capital theta, okay? So obviously I used it, but I'm just reminding you that we usually put the capital when we do probabilities, right? So we do capital Y, capital X, but because we're using these Greek letters, let's just try to use the capital version of it. So that's what it means. The probability of theta less than 0.3, it's close to 1. The probability between 0.3 and 0.7 is also close to 1, and the probability of being larger than 0.7, it's also close to 1. So three different, very different scenarios. So these are the scenarios, so these ones, okay? So this is the first one. So it's very concentrated between 0 and 0.3. Not everything, but most of it. The other one is concentrated in the middle. That is when alpha and beta are equal, and in this case equal to 11. And the third one is when everything is concentrated on the upper part, so larger than 0.7, it's the majority. So obviously these cases are pretty much disjoint, not completely disjoint. So we cannot entertain them at the same time. So basically, I will go back. So this case, the one that I was considering, is basically this one, okay? So the person that is assessing this specific example that I mentioned is sticking with that one. But obviously this is going to be a kind of a personal thing. Everybody, or the statistician which is doing the analysis, will have to choose either any of these or another one. I'm just giving you three very different options. So this is not a matter of sweeping different values, because it's like choosing the alpha, the significance level in a hypothesis test, is not something you can change along the way. It's something you just need to do before the analysis starts, preferably. So it's the same here. This reflects your prior knowledge about the parameter theta star, okay? Independently of the data. You cannot do this after using the data, because it's not only cheating, it's just going to make the analysis more complicated, because everything depends on everything. So anyway, each person or each analyst should have to choose, for example, either of these three, but not the three of them, or not two of them. And then I just choose three extreme examples, which, as I said, they are quite disjoint. Okay, so let's now do probability. Let's go back to probability courses, and let's see now how can we combine these two sources of information, because remember, I still have my sample. Okay, so this is where I'm going to start using the color coding. So I still have my independent sample, yy to yn. So I'm going to use blue for that one. So I have my sample, and I had my prior distribution, okay? And the prior distribution reflects how much I believe it's a value of theta star. So it's called a degree of belief. That's basically how we're going to call it. But it's just a distribution. So how can we combine it? So let's just do it, okay? So let's just combine it. And to combine it, let's just use probability, okay? So what we got? So we got f of y of theta. It was what? It was theta to s of y, 1 minus n minus s of y. We know what is s of y. And then we got now f of theta. It was, sorry, let me just make it a bit more to the left. And we got f of theta is theta to alpha minus 1, 1 minus theta, beta minus 1. And what I'm going to do here is I'm going to start using this symbol now because it's what I'm going to be using. So that symbol means a proportional to, okay? So I'm not going to, the constant which I divided, that beta function, doesn't depend on theta. So you will see it's not going to be very important to know exactly what it is in this particular example. So the density of the prior density of theta is proportional to, that's what this symbol means. So let me just write it down so that you don't forget. So what this means is proportional. Okay, proportional to. So let's just use probability then. So this is what I promised. So first of all, let's just make sense why what we want is this. So we want f of theta given y. Actually, let's just calculate it and then we have time to think while I'm doing it why this is what it makes sense to compute that thing. But now we're using pure probability. So just going to be a little bit informal, but hopefully you're okay with that. So conditional probability. What is the definition of conditional probability? Conditional probability is the probability of the joint, or the joint probability divided by the marginal probability. So we got f of theta y divided by f of y. Okay? So remember definition of conditional probability, or even conditional density, depending on the case, but it's the same. And then I flip, okay? And flip means by using the same definition again, we got f of, sorry, the other way around, is f of y given theta, yeah, times f of theta, and then divided by f of y. Exactly. So I'm using the conditional definition twice, right? So the definition of the conditional of theta given y, I use it here, and then from here to here I use the definition of the conditional of y given theta. They both have the same numerator but different denominators. I just move things around. Okay, so this formula, I mean, I just come up with a formula which you might just have used before. It's called the Bayes formula, or the Bayes theorem. I mean, it's been put now with bells and whistles, even though it's a very simple theorem. It's just a formula which you can just show using simple probability. So this is what is called Bayes formula. Okay, so Bayes formula, or Bayes theorem. So, look, theta is just a variable, but it's my assessment of theta star. Is how much I believe, for example, this is the prior distribution and I got my sample, but this is given the sample that I've got, what is my degree of belief, or my probabilities about theta star that I've got after observing my sample and after including my prior distribution, okay? So let me just write that down. Yeah, okay, so let's just write that down. So this is the, let's say this is the updated, and this is updated is after observing y, the sample y. So it's my updated belief about theta star. So let's just say that f of theta, it's my prior, or our prior belief about theta star. Okay? So now I'm just defining notation, but it kind of makes sense. So the prior distribution is my prior belief, and again, it's just words, but it's scientific anyway, is what we think it's the value of theta star prior. Okay? So it's those, that one, the beta function, which we know the shape. And after I observe the data, that what is conditional on observing the data, this is pure probability, we update our belief after observing that, and now it's different. So let's just see what happens. So the formula is there, but let me just remind you how to do that. So what is going to happen is now I'm going to apply the formula. So I got a formula for this, and I got a formula for the other one, and then see what happens. Okay? Yeah. So let me just continue. Okay? Okay. So just bear with me. Okay. This thing went crazy, sorry. Oh, there you are. Okay, so let's just continue with that. The formula is as follows. So we got my f of theta given y. It's going to be now theta s of y, 1 minus theta n minus s of y. And then I've got my beta distribution is what? Theta alpha minus 1. 1 minus theta beta minus 1. And I'm going to use the same symbol again. And why? Because, let me just go back to the other one. This guy here, I'm just going to do it in red then. This guy here doesn't depend on theta. So this is the normalizing constant I was telling you. So this is a variable of theta, a function of theta. This guy is not a function of theta, so it's just a constant. I'm just going to keep ignoring those constants. I just want the parts which depend on the variable, which in this case is theta, or the parameters. Okay? So that's why I'm using the proportional to then. Okay? But the following part, it's equal to, so that part, as it were, let me just do that. So that part is equal to theta, and let me just do this, is alpha plus s of y minus 1, and then I've got 1 minus theta, and so this is, you need to count what happens with the other one. So 1 minus theta, so it's n minus s plus beta minus 1, so it's a bit longer. Yeah? So this is n minus s plus beta minus 1, yeah? Yeah, so at least just to get that it coincides with what we got in the formula. And look, in the formula I'm just using that because it's exact, but I just want to get you into the habit of doing it that way, because this is just luxury, which we are not going to afford later, to have all these integrals in closed form. Okay, so if you think about this, let me just write that like this. So let me see if I have a notation for that. No, I haven't got a notation, but what I'm going to do is I'm just going to put these ones together, okay? And let me show you that it is like another beta, right? Because remember, the beta distribution, or the beta density here, so this one, the one that I'm highlighting here, this one, it's always of the form theta something minus 1, 1 minus theta something minus 1. And this is of the same form, but now the alpha is not alpha, it's alpha plus s, and the beta is not beta, it's n minus s plus beta, okay? So that means that the new variable, or the updated belief as it were, so theta is distributed as a beta distribution with alpha plus s of y, comma, n minus s of y plus beta. And this is conditional. Sorry, I made a big mistake here, because this is conditional. So theta given y is like that, and theta prior, it is beta. Now to use the notation, it's alpha beta. Okay, so let's just give it just the names. So this is going to be called the posterior distribution, and this is the prior. Okay, so this comes from just notation, which means like before and after, right? So prior means before, posterior means after what happens, a posteriori. We're going to use this kind of a Latin notation just because scientists will like to be pompous in that sense, but it's just what it means, is what happens before I observe the sample and after I observe the sample. And those are beliefs or distributions. So I'm just going to use now distribution. So I'm going to stop calling it belief. Belief is kind of the way we communicate with people, which is not a statistician or a scientist, but it's really what it is a distribution, right? So distribution here is kind of belief, right? But it's a scientific belief. It's just not hunches. And how I know that is just because of the formula, okay? Because anything will have to have a function beta like that. So I'm not going to write it that way, because as I said, later on you will realize that it's just a luxury to get the formula that I got here in the bottom, right? So that this formula, this integral from 0 to 1 of that is equal to that beta. I don't really care too much. I care because it makes things a little bit simple, but I'm just going to stop worrying about that, because all the methods we're going to see to deal with these distributions, with these posterior distributions, are going to be designed so that we don't worry about those constants, okay? So let's stop worrying about them. Even in this case, they are easy, okay? So we're going back to probability in the sense that most of the operations we do are really probability operations. The likelihood is not clear as a probability, because I never call it a probability as a function of theta, but in this case I'm going to use this posterior distribution as a function of theta as a probability, so I can use all the operations of probability, which is one of the gains I get by using this Bayesian approach. Okay, so let's just look at examples. Okay, so this is a really nice plot, which I need to show it to you because there is a lot of information rather than try to plot it myself. And this is the color coding which I was saying. The yellow one, it's, even though I didn't use yellow there, I used a kind of an orangey one just because it's difficult to see. But the yellow is always the prior. So these are 9 different situations, okay? In practice, we just get one of them. But let's just think about these 9 different situations. So the yellow one, it's the prior distribution or the prior density. The blue one is the likelihood, which we don't normally plot. We plot the log likelihood, but let's just plot the likelihood here, because that's the one we are, let's just use the color coding here. So the likelihood is this guy, the prior is this guy, and the green one is going to be the posterior, which is the whole thing, okay? So that is the color coding. So green is the posterior, so the thing on the right hand side of the equal sign. I plotted there. The yellow one is there, and the blue one is there. Okay. So, and this is how we're going to measure, at least visually in this very simple example, how the information is combining itself to get the result, which is the green one. So the green one is what I really use, but this is telling you how it's combined. So before looking at the numbers, let's have a look just at the plots, okay? And there is a lot of issues here, so let me just go slowly. So for example, this case, this is the prior. So it's the assessment which I started this lecture, right? So I said somebody comes and tells me that the prior distribution of theta star, it's going to be somewhere concentrated in a small values, less than a half, as I said. So that's the yellow one. The data tells me something else, because the MLE, it's about 0.9. So that means in a sample of 100, 90 times we observe 1. So the likelihood is going to be like that, which is really contradicting what the prior says. The posterior comes and conciliates and gets something in the middle. I mean, as you would expect, that's what's going on, because it's a product. So two things are multiplying, they are positive. None of them is 0, because if one of them is 0, then it kills everything, right? So that's why we need to be careful in not assigning 0 probabilities. But that is not the case. So this thing is very close to 0, but not 0. This blue thing is also very close to 0, but not 0. But when I combine them, we get something in the middle, okay? Because it's a product of positive numbers. And below 1 as well. So, so that kind of makes sense, that the posterior is trying to conciliate. This is my prior knowledge. This is my data. You get something in the middle. This is in some sense the worst possible case, because it's not that the information is contradictory, it's what you got. And it's contradictory, but it's not that it's bad. This is what we get as a result. This is a more positive case in which prior and likelihood agree. So I cannot even see, well, I can see it, sorry, that is the yellow one. So the prior, it's very concentrated on 80 to 90, so it's very possible that the probability of 1 is quite large. The likelihood agrees that, because the sample got something about the same, 9 out of 10, 90 out of 100, and the posterior is just somewhere again in the middle, but in a different sense. So the posterior is a bit narrower. So remember variance. So a distribution which has large variance is more spread. A distribution which has smaller variance is more narrow. So the green one is more narrow because I learned a little bit. So the mean, it's the same, but the variance is a bit smaller because I got more knowledge. So the variance, in principle, you would like it to go to 0. Obviously, that's never going to happen, but that's what you will tend to. The perfect knowledge is a distribution of a mass in a point, and that's theta star, right? But this is telling you prior it's very concentrated in this interval. Likelihood is also very concentrated, so therefore it's posterior. It's also concentrated, but a bit more than each one of the two previous ones, the likelihood and the prior, because you have accumulated, like in some sense, twice as much information, the prior and the likelihood. And there are cases like that, so all of the cases in the diagonal are like that, just in different values. So here prior and likelihood agree, but in the middle. Here prior and likelihood agree, but in this other end. And in the other cases is when the posterior is trying to conciliate the difference between different assessments, right? So for example, this one, the prior is somewhere in the middle. The likelihood is says something small, so the posterior is somewhere in the middle, but you see there is more overlap than here. Here is almost completely disjoint, prior, posterior, and likelihood. So let's just have a look at the numbers now, because the numbers now also are going to give me some information for this particular example. So let's just see. S is the sum. Let me just remind you that. What is S? S is, well, I can write it here. So S of y is the sum from I equals 1 to n of yi. And remember, yi's are only 0 and 1. So here is the number S, okay? N, I need to tell you what n is. So let me see how much n is. In this example, n is equal to 20, okay? So let's just write that down. So let's just do an example. And the end example is going to be that n it's equal to 20. So that's fixed, so I'm going to write it down. And these alphas and betas are written in the plot. Okay, so then we don't have to go back to the code. We can just see them. Okay, let me see, sorry, because I have two plots like this. So this is the one I want to look at. So now let's have a look at this plot again, but now looking at the numbers. Okay, so there is 20 trials, and 18 of them was 1. So that's why the likelihood is so close to 1, right? Because 18 out of 20, it's 0.9, right? So it's 9 out of 10. So for example, same here. So when we go by rows, S is equal 18, 18, 18. So the likelihood, look, the likelihood is a bit bigger here than is here, than it's there. So this is when I'm playing with the normalizing constant. So remember, the normalizing constant, which I'm using there, I'm playing with that to try to get the height of the likelihood different. So what I did is every time I see a likelihood, I match the height of the prior. Because the prior integrates to 1, but in general, the likelihood doesn't have to integrate to 1. So this is a trick, which again, we'll have to get used to it. And it's, well, not a trick, it's just using the mathematics that when I'm thinking about distributions which are proportional to a constant, I can just move them up and down within reason. And obviously, this is not to cheat, because in the end, we have to normalize back everything to something which integrates to 1, which is the posterior. But just for plotting, that's why this guy looks a little bit higher than this guy, even though it's exactly the same likelihood. Because remember, if S is equal to 18, N is equal to 20, that formula on the blue one doesn't change. The only thing I'm changing is I'm multiplying by a slightly different constant under this proportionality. Okay, so getting that aside, each row, it's a different sample. 18, 10, and 2. So now you see why. The one which is 10 is in the middle, right? Because it's 10 out of 20. It's around 0.5, 0.5, or 0.5 of different heights. Remember, the blue one always matches the yellow one. The blue one always matches the yellow one, just for visual purposes, really. And the first one, S, is 2 out of 20. It's just the opposite of the other one. It's 0.1. So that's what is concentrated here. And then the priors are now, you know what they are. They are concentrated here, concentrated in the middle, or concentrated on the top. So that's why 3 cases for the prior, 3 cases for the likelihood or for the sample. So that gives me the 9 cases we have here. But in practice, we only see 1. But this is what we're going to use. So we need to use the green distribution. That's the output of Bayesian inference. That is, we finished, okay? We finished means we are going to use the green distribution. This is just an explanation of how the information has been combined, or where does it come from, and which part contributes to what. But what we're going to use is the green one, okay? So let's just write that down. So in the example, so this is just for the example, okay? But so we use f theta given y for inference. So this is Bayes, right? Or Bayesian inference. What do we do when we have not Bayes? What do we do before this lecture? We always use only the log likelihood or the likelihood. That was our only source, and we calculate gradients and Hessians and all the rest of it, and we did hypothesis testing. So for the other one, we use the likelihood. I'm going to use log likelihood, but let's just be similar. So we use the log likelihood for inference, and this is the classical approach, okay? And the classical approach, it's what is called frequentist, and this is just a name, okay? Frequentist is because all the time I keep looking at, for example, confidence intervals is if I got a repeated sample of the same thing 95% of the time, something happens, and a hypothesis test is the probability of type 1 error is if we repeat this sample many times, then the probability of getting the thing wrong, it's also 0.05% or whatever. That's what is called frequentist, okay? Because we use sampling distributions on the repeated independent samples. So this is the difference. So for inference in a classical sense, we use the likelihood. For inference in a Bayes sense, we use the posterior distribution, right? So by the way, remember, this is the posterior distribution, or the posterior density. It's just going to be posterior everything, posterior mean, posterior variance, all of the usual. Even we're going to have, if you like, posterior gradients and Hessians, if you like, but this is just, it has to do with the conditional distribution of the parameters given the sample, okay? So let me see what else I have got here. There is a bit of things which we are going to learn along the way, which is what is the interpretation. So I think I'm going to do that next time, because I don't want to have I don't want to cut the discussion. So this is another example, and the prior is fixed, but the only thing I change here is the sample size. So let's just see what is the effect of sample size. The sample size in the previous example was 20. Now is 60, okay? So look. Now, if S is equal to 54, so that's again 90%, right? Because 54 out of 60 is 90%, and 6 out of 60 is 10%. So the percentages stay the same, but the sample size increase. So the yellow curves are the same as in the previous plot, but the blue curves, and therefore the green curves, because the green curves combine everything, are different. And then you see the only thing that happens is that the blue and the green got a little bit narrower. So obviously, when you have more sample, your variance tend to go not exactly to 0, but it gets narrower, or at least you would hope that happens, and therefore the posterior distribution is a bit more concentrated because you have more information. So if you compare, remember the green one is the one that we want, for example, this green one with the one that we have before, the only difference is the sample size, and look, this is whatever, spread this much, but when I increase the sample size and everything else gets fixed, it got narrower and a little bit moved to the right? Just because the sample size doesn't have a symmetric effect, okay? Just because, remember, we have the prior is not symmetric, so the prior is telling me that about 2 out of 10 you get once, that's the prior, and the likelihood says here that is 90%, so the prior got a little bit more to the right, and the reason is the sample here, it has more weight than the prior has. So the discussion I want you to have a look, to read, it's in the text. Okay, let me show you. Here in the text, it explains to you what these alphas and betas, actually, for this example, you can interpret them, not exactly alpha and beta, but a function of alpha and beta can be interpreted as actual samples. Not exactly samples that you observe, it's like virtual samples, hypothetical samples. Okay, so this is the reason why these plots, now they're starting to move around. So why this green plot was in the middle in the other plot, and now it's on the right? It's because the alphas and betas weren't as big as a sample size than 60, okay? So this is when you need to start to combine kind of how much information is in the prior, how much information is in the in the likelihood. And so when you weight them by the Bayes theorem, which does the multiplication, one of them is going to start to have more weight. And this is, you see, if you think about pooling, the blue one is pulling the green one each side, right? Rather than the yellow one. So think about it like pooling. So in this one, the pool, it's equal, right? So this one is trying to pull this way. The blue one is trying to pull the other way, but they are equally strong, so then you get something in the middle. But here, the blue one is winning, right? Because it's pulling the green one each side, and the reason is because n is 60, but the thing that you need to read a little bit is why there is a hidden n here, which is smaller than 60, and that's why it doesn't have enough weight to pull, basically to pull its weight to its side, which is the left-hand side, okay? So I think, let me just finalize with the more slides that I have, which is just a summary of what happened in here. So there you go. So this is just a summary. This example, it's very simple, and most of the things are, that's what I used it. Everything is closed form, and then you can see these trade-offs and compromises between data and prior, but let's just see in general. So I call it the classical approach is what we've seen so far. I never call it like that, but now when we have the Bayesian, then it's worth calling it something a little non-Bayesian, if you like. I think that would be probably more appropriate, less politically inappropriate. I'm saying that because some people say, no, I'm not Bayesian, but I'm also not frequentist. So let's just not get into that discussion and stick with that name. It's about sources of information. So in this approach, so far, before today, we have two sources of information. We got the sample, and we got the model, because the model has information. Remember, one of the reasons I know it's hard for the learning, but to always entertain more than one model, because remember, last lecture I was talking about the Weibull and the generalized Weibull and the exponential, etc. We always entertain different models. So each model has a different information in it, which is not the sample. We feed the sample to each model, so the model in itself has information. So information comes from the sample and from the model, and from that we do everything. We do MLE, we do gradient and Hessian for different values of the parameter. And the way we break things down is that theta star is fixed but unknown. Remember, that's what we've seen. The observations are just a distribution of y, and then we use the log likelihood to do everything. So this one I'm going to go quickly, because that's what we've done so far. The only thing I want you to emphasize is that theta star is fixed, because it's not known, but it's fixed. It's 0.5. I just don't know what it is. Remember, when I simulate, I know I can simulate 0.5, but I just need to ignore that when I'm doing the analysis. But it's fixed. It's unknown, but fixed. And this is what I'm emphasizing here. So the parameters are deterministic. There is no random about them. And the data is random, because I use the sampling distribution, and that's the frequentist part. Okay? So I'm just establishing notations of what I've done so far. What is the new notation for the Bayesian is that there are three sources of information. We got the sample, we still got the model, but now we got the prior. Okay? So everything is playing a role. And in my plots, I only use like two, but the likelihood combines really the model and the sample at the same time. In some more complicated models, we kind of separate a little bit of the pure sample and the model, but obviously that's obviously more advanced. So at the moment, the likelihood combines the sample and the data all in one go. And then the distributions now, the data is going to be fixed, because I'm going to conditional on y, and the parameters are going to be random. Theta star is still unknown, but it's random. And why random? Because I give it a distribution. I said it's a beta. And it goes from 0 to 0.3 in one case, etc. So that's the prior. We got my likelihood, but now the likelihood is a conditional density, and I got the posterior distribution, which is this guy. And this is my symbol of, which I obviously write it down very badly, but it's like kind of chopped infinity, right? Or like a tweezers or something. It looks more like a forceps, right? So anyway, that's just so that, just in case you haven't seen this symbol, is the same one that I tried to plot there. That's the proportional one. And now what we're going to do for the rest of the course is what are we going to do with that posterior density? So obviously the best is to get the whole posterior density, but sometimes we are not going to afford that. It's like when the likelihood we are going to use only summaries of it. So for the likelihood we use the maximum likelihood estimator, the gradient and the Hessian essentially. But now we are going to use the maximum, which has a name. It's called the map. Very popular now in now very advanced machine learning techniques, because when the problems is quite difficult, then you cannot afford to get the whole sampling, the whole posterior distribution. You just get the maximum of the posterior distribution, for example, or at least you just want to do that, or expected values. And these are posterior or conditional expected values. Okay, so that's it. So that's actually what I got for today. So this was just an introduction. Next lecture, I'm just going to go into a little bit more theory, and then we take it from there, how we're going to deal with these posterior distributions. And so final thing is next week, I'm going to release the coursework. So if some people have already sent me an email either telling me this is my group, and then just give me the names, or if you don't have a group and you want me to assign you randomly to a group, just tell me so that I can do that. So if we can do that by Friday, so that on Friday I can just have the final groups before the coursework is released next week. Okay? So that's it. See you on Friday.